Hi, this is Michelle Cullen, and I'm here to cover what we've learned this week on telescopes and astronomical instruments. This week you learned all about instruments that astronomers use to extend their vision beyond our solar system to the stars and the galaxies. We learned that visible light, or white light, that comes from the sun is actually a mixture of all the colors of the rainbow, and when you view it through a prism or through a diffraction grating like you did in the spectroscope in this week's lab. But when starlight is viewed with modern telescopes beyond the visible, they can detect light in all wavelengths, from radio to gamma rays, making it possible to see sunlight in a whole new light. Modern astronomy has built newer and more powerful telescopes and placed them in the most desirable location, whether they're on a mountaintop or orbiting the Earth above in space. Despite modern technology's advances, a telescope's function is basically a light bucket. It's to collect faint light from astronomical sources, whether that's a planet, a star, or a galaxy, and to focus the light onto a detector. And it's interesting to note that your eye is actually a detector. But there's also photographic plates, the old school way, and the modern CCD, which we call digital charged coupling device. And CCDs are pretty cool. And we also learned that the larger the aperture, or the opening of the telescope, the diameter of the telescope, that the more light can be gathered. So the longer time the telescope points to the object that we're looking at, the more light can be gathered as well. So we say the ability of a telescope to capture light, it's mostly closely related to its diameter and secondarily related to how long you can focus it. We learned that a refracting telescope uses an objective lens to concentrate and focus incoming light to a point. Binoculars refract light through their glass lens as well. A telescope that uses a primary mirror to concentrate the incoming light is called a reflecting telescope. Most large telescopes today are reflecting, and they have many advantages over the old-fashioned refractors. The reflecting mirror can also be made larger and lighter than a glass lens of the same size. Mirrors are easy to support, and they won't distort as easily as a large chunk of glass, which can actually change shape over time. It's interesting to note the Hubble Space Telescope, which is a reflecting modern telescope, has taken images, of the oldest galaxies and the farthest things away. And it's interesting to note that because it's only 2.4 meters in diameter, not that big, it cannot resolve an image of a flag that is on the moon. What? The Hubble can't take a picture of the flag on the moon? Nope. It doesn't have enough resolving power. It would take a telescope with a 200-meter diameter to clearly see the flag at the distance that it is from the moon. So the Hubble works by timing. It has a beautiful, clear opening and mirrors, and it doesn't have any dust up there in space, and a long time can capture very distant images of galaxies photon by photon. It can take up to a couple weeks to get those images. We also learned, looking at some very large reflecting telescopes, some newer ones, like we've got the 30-meter telescope in Mauna Kea, Hawaii, and a larger one even in Chile. Those were placed high up on the mountaintops above the turbulence of the clouds and the atmosphere to be able to observe the visible and infrared, because visible and infrared and radio are what make it down to the Earth. And there's also some modern technology, adaptive optics, that moves a small flexible mirror many times a second with computers to correct for air turbulence and other distortions that can make these new and our old telescopes even better. This, along with modern digital technology of CCDs, like those ones found in your digital camera or cell phone, really improve modern telescopes' performance. Astronomy's gone through major revolutions since the 1970s with the development of the CCDs, and the Hubble was proposed not long after that, actually, by Spitzer, and it took until 1990 that the Hubble was launched from the space shuttle and put in space. So there's many new telescopes that orbit around the Earth to look at light that doesn't get down to Earth from the lab. You remember that only a little bit of ultraviolet and infrared and all of the radio reaches sea level. But when it comes to higher energy, thank goodness, gamma rays, X-rays, extreme ultraviolet, and a lot of infrared get blocked by our atmosphere. And and microwaves too. It's probably a good thing. Those are best seen by telescopes placed above 10 kilometers of the Earth's atmosphere. It's cool to know some of these space telescopes. There's new ones coming out all the time in our textbook and online. We've talked about the Hubble a lot, and there is the 2021 James Webb Space Telescope coming up to replace the Hubble. And then we've got infrared space telescope. We've got the Spitzer, and we've got the Chandra, which looks at X-rays, and the Fermi, which looks at gamma rays. So those are some major ones to know. And let's just change gears a little bit and wrap up this chapter by taking a tour of different kinds of light that can be gathered with different wavelengths if we were viewing our sun. And so let's start with the really high-powered ones. Let's look at those short, energetic X-rays, high-frequency X-rays. And when you look at the sun, it turns out that it actually is radiating in X-rays, and you can see that they're coming from the corona, which is the outermost, hottest visible layer of the sun's atmosphere that radiates into space. And through X-ray, you can see that pretty clearly. You don't have to wait for an eclipse. Now, when we look at a little bit lower wavelength, we can look at the extreme ultraviolet. And again, we're in space. There's a telescope called the SOHO, Solar Heliospheric Observatory, and it looks at that ultraviolet. And we can see when we look at the sun, it's looking at the chromosphere, and we can look at the hotter, more active regions showing up brilliantly in extreme ultraviolet. It's not necessarily purple. We've changed these colors to make them look like visible light. But when we do look at the sun in visible light, it's just kind of white, and it's rather boring. We can see that there's a smooth photosphere and maybe some small dark sunspots, and that's where it's cooler. When we go down a little notch, we're going to look at infrared, and we can use infrared telescopes, and we can show that the sun does radiate mostly in infrared, which is the heat. And by looking at it, we can see the surface temperature variations. So that's pretty cool. And then if we look at even longer microwave and radio waves, you can look at and learn that the sun is actually one of the brightest sources of radio waves in our sky. So you can't really hear any music from the sun. It's all static radio waves, but it's still blasting us with different frequencies of radio waves. We can study through powerful radio telescopes linked together, either huge ones or ones that are multiple linked together in interferometry. So all of this real-time data viewing on our sun in different wavelengths is useful to predict potentially damaging solar storms that can wipe out electronics. Well, I hope you enjoyed learning about telescopes as much as I do. I hope you have one, or you can get out and look at the sky with your telescope or a neighbor's or a star party. And you can find that these giant eyes help us observe our cosmos and are pretty cool. I look I also look forward to reading your reflective journals this week and find out what inspired and confused you. And if you've taken notes on all these learning objectives, I'm sure you're going to do very well on the quiz. So this is Michelle Cullen signing out for telescopes this week.